can you hear me? More or less. Okay. No, thank you everybody for being here. So I want to start by, I'm very happy to be here because I want to tell you a little bit my story, 2-3 minutes before I start talking about this topic. And actually, the warm-up was the very first scientific event which I ever attended. So it was in 2013, and it was the very first edition of the warm-up. We were in Barcelona, and I didn't know anybody, and my advisor couldn't come from London, so I went alone, and I mean it was just so nice that I got to meet a lot of people, and I already made a lot of friends with whom I could spend time during the conferences. So it was a very good experience, and I'm still friends with many of the people, and I don't know, maybe some of these social and scientific contacts didn't seem so useful, but in the first years. But then, for instance, this year I'm working with Michele Starnini, who some of you might know, and he's a very close friend of mine, and I met him in Barcelona. He was organizing the warm-up, and we just went for beers for many years together, and now we're writing a paper together. So I mean, I just think it's a fantastic event, both socially and scientifically. So so today I want to talk a little bit about a topic on which I've been working on in the last 2-3 years. I'm not the only one in the scientific community who has been working about this, on this topic. Of course, unfortunately, today I'm just going to present, mainly going to present the things I've been working on, but I want to stress that there are many other people who are doing interesting things on the same topic. The idea is that to work with these complex networks, which are a bit more complicated than traditional complex networks. So I just don't want to start straight going into the issue of what a higher order network is. I would just like to take a step back and motivate this a little bit. So I mean, I studied statistical physics in Rome, and I come from the general field of complex systems. And I mean, when I talk about complex systems, I always like to take a step back all the way down to this very famous piece, which was published 50 years ago in Science. So this year we had the Nobel Prize, last year we had the Nobel Prize in physics. But I mean, it was not those 3 awardees were not really the first people who were working on complex systems who received the Nobel Prize. One of these persons, for instance, was Philip Warren Anderson, who was working on condensed matter physics. And I mean, in years when the most interesting experiments were considered those about, you know, trying to find the tiniest particles of which everything is made of, he was already warning us that the reductionist hypothesis does not imply a constructionist one, and in particular that the behavior of large and complex aggregates cannot be understood as a simple extrapolation of the properties of a few particles. So, I mean, we are all convinced that this is important, this matters, and this is why networks are the backbone of complex systems. And so networks, we use them typically as the infrastructure. No, it can be a physical infrastructure, real infrastructure. It can be an abstract infrastructure, so a way that we model our system. But the important thing is that while this represents somehow the infrastructure or the structure of the system, this is very important to model the emergent collective behavior that takes place into the system. It can be anything. We know, from the spreading of social contagion to a disease. We have cascades in power grids. We have also good things like the emergence of cooperation, for instance, in our societies. And if now, what is the issue? The issue is that we know that complex systems are very hard to understand sometimes. They're especially hard to control and predict. So the idea is that the more accurate will be our architecture, the better will be our ability to understand, control, and eventually possibly also predict what is happening in them. So this is why over the last decades, I think, since the very beginning, actually, I think network scientists have started working on enriching our understanding of what a network is. So a network is surely a collection of nodes and their interactions. But what type of information can we add about their interactions? Well, I mean, since the very beginning, people have started thinking about adding weights, for instance, describing relationship of different intensity, adding directions with a source and a target, or adding signs, no? So we can have a positive or a negative relationship into the system. And then a bit more recently, especially driven by the deluge of new data that we have had, especially starting since the early 2000s, I think. Network scientists have started working on a slightly more complicated mathematical framework. So, for instance, a lot of studies now have been focusing in the last 15 years on temporality, and I mean, for instance, Yari has done a lot of work on this. He has written the first important review on the topic, and then after that, I would like to mention multi-layer networks, where we have links of different types which are embedded into different layers. And I mean, sometimes these tools have become so natural that we do not really need to write in the title every time the word temporal, time varying. They are just a toolkit that every complexity scientist should have. So I think that right now, what is the next step? Well, probably the next step, at least I think, an interesting next step is trying to understand a little bit how to model networks where interactions can be among, how to properly model networks where interactions can be among a group of nodes and not only pairwise interactions. But I think the final goal of this is not to create a separate network science, of course. I think the goal of this is just to extend the toolkit and the type of analysis that we can do when working with our data. So these group interactions or higher order interactions are ubiquitous in the sense that they have been found in many different places. For instance, in producing successful drugs, in network medicine or network biology, you need to combine more than one item at a time. In social systems, it is quite natural that many interactions are actually not pairwise interactions, but we meet in group. The coffee break, we saw a lot of groups of people meeting. And in ecology, often the introduction of one species into an ecosystem can mediate the relationship with the other two. Or there's a lot of work, for instance, on neuroscience that focuses on functional connectivity, the activity of these different regions. And what people do is that typically they focus on pairwise connectivity. So if two regions activate together, we put a functional link between them. However, in many cases, actually, it's more than two regions at a time that activate together. It's like a complex set of regions which is activating together. So how can we properly describe these group phenomena, for instance, in this type of systems for which we have time series data? And I was saying that how can we model group interactions properly? And of course, I mean, modeling group interactions is not a very new idea. And we, network scientists, complexity scientists, we think we have been doing this for a long time, already through the tools of networks, traditional graphs. But there are some shortcomings. So here, I show you a very simple example from a co-authorship network where we have Alice, Bob, and Claire, who decide to publish one paper together, which means that in our co-authorship network, we will have a link. And then we have Bob and Claire who publish another paper, and also Alice and Claire, and this will be a triangle in our co-authorship network. It is clear that this is very different from the situation where Alice, Bob, and Claire decide to join forces and write a single paper together. And this is different, not only from a structural point of view. So these two structures, with traditional network encoding, these two structures are impossible to distinguish. But I think maybe more importantly than the structure is actually that, as I said at the beginning, we study the structure to understand dynamics, to understand collective phenomena, to understand emerging behaviors into the system, especially if we are complex system scientists. So the problem is that if we are not able to distinguish the structure, we cannot give different dynamical meanings to these objects. For instance, in all those phenomena where we have contagion processes and we want to model contagion at the micro scale, and we know that, for instance, social contagion is different from biological contagion because biological contagion seem to work at a pairwise level. So I meet somebody and I have, and every time I meet somebody, I have this person is an independent source of infection and I have a given pairwise probability to acquire the disease. Instead, for social contagion, we believe experiments support the idea that actually this works in a different way. So I am with a group of people and somehow I evaluate the ideas in my neighborhood. If enough people are infected, I will acquire the disease. So if we cannot distinguish this, how can we properly model group dynamics at the micro scale? So this is the starting point of the question. And the problem with networks, just in one word, is that actually links, which are our traditional building blocks to describe interactions, are inherently limited to describe pairwise interactions only. And the idea, very simple idea, is that actually to properly model group interactions, we should use, in general, some other higher order building blocks, of which links are also part of. But we can have these field triangles, which encode free body interactions, or possibly field tetrahedra, which encode four body interactions, and so on. And so yes, here, this is jargon. I mean, I'm not sure. Sometimes the order, these objects are called simplices, and sometimes, for historical reasons, I don't want to go through this. Sometimes the order of these objects is n-1. We have n nodes interacting. Some other people just like to say n, whatever. I mean, as long as we understand, it's just a convention, after all. So there are, as I said, I mean, we are not discovering a new idea. No, I mean, group interactions have been there for a long time. For instance, what we could do with the old networks. So, well, I mean, a good framework to study interactions beyond the pair, which is very famous, is the framework of network motifs. So, trying to understand, try to evaluate subgraphs among more than two nodes at a time, which are found in the real system at a frequency which is higher than one expected by chance. I think this is a very good tool, and it doesn't align exactly with the idea that we have in mind to model the actual single interaction as a real interaction, so free for people and so on. Then there are cliques. There are cliques that somehow we can think of as a special type of motifs. The problem with cliques, it's not a problem, it's just, I mean, a limitation is just what I was showing you before with the very simple example of the triangle. No, we have a clique of three. Is this an empty triangle? Is this a triangle which emerges from the accumulation of different pairwise interactions? Or is this a field triangle, which is a true higher order interactions? And the other very clever idea, I think, is the idea of to use a bipartite graphs, which I assume most of you are familiar with, where we have two sets of nodes, and you can only have links across nodes belonging to the two different sets. But this is a very particular type of bipartite graphs. So not all nodes represent real units of the system. So this is not, for instance, like in ecology, where you can have a, I don't know, a plant pollinator bipartite network, where basically one set of nodes are your plants, and the other set of nodes is the insects which are pollinating your plant. So this is a different type of bipartite networks, where one set of the nodes does not describe units, but describe interactions. Okay, describe the groups. And I think that this is a very good idea to describe groups. It's just doesn't align exactly with what the way we are used to conceptualize our interacting system. Now, where nodes are the units, and then there are the interactions on top of this. So by putting together those higher order building blocks that I mentioned before, what we have is we have not a graph, but we have other things. And for instance, what we have is we have what is called a simplicial complex. So a simplicial complex is obtained by putting together those simplices, those collections of higher order interactions. It is a framework which is heavily used in applied mathematics in particular, because there are some specific properties here. So simplicial complexes are particular collections of higher order interactions, where if you have a free body interactions, like this one on top, automatically, it also means that you also have to have all the subfaces, the sub-interactions, the smaller groups which are contained into this group. So you can have all the pairs, and for instance, and so on. So this is not a very flexible framework, but I mean, it is heavily used because it allows you to, it gives you access to some powerful framework, such as, for instance, the one of topological data analysis, which allows you basically to get insights into your data by exploiting the shape of the data. So I don't want to talk about this also because I don't really like to work with simplicial complexes. But this is just to mention to you that these exist. And what I like to do is just to work with, I mean, for me, interactions are just interactions. If there is an interactions of free, why I should have also the interactions of between the pairs of the triangle. So this is what is called basically relaxing this particular condition on the subface. What we have is just collections of these things, which is what is called an hypergraph. Okay, very generical. So 2 years ago, together with some friends, we wrote a very long review on the structure and dynamics of these systems beyond pairwise interactions. I titled that networks beyond pairwise interactions and not higher order interactions. Why? Because, I mean, at the time, especially, I think that this term higher order interactions is a bit of a jolly. It's been used for many different things. For instance, it has been used a lot to describe temporal systems, temporal networks, where you have memory. Okay, so basically it's a temporal unfolding of the system, temporal evolution of the system, where there are particular correlations, non-Markovianity, and things like this. So I wanted to distinguish a little bit this type of field from the others. However, I think there's still a lot of confusion into the literature, and when I can, I directly use the term beyond pairwise interactions because I think it's clear, but there are satellites which, I don't know, I see yrCSS or a NetSci, other conferences, this term higher order sometimes is used very specifically for something, sometimes it's used very generically. It might not always mean what you think it is meaning. So let me see. So today we just have a little time, so I don't want to take forever, and I just want to give you some insights, very simple things focusing on the structure of these systems that we can learn about these systems. And there's a whole wide literature on dynamics, and I will point out to something, but there is also the upcoming conference where I see there are a lot of parallel sessions devoted to this topic. So I will point out some interesting talks on the matter. So, I mean, one thing is reconstructing groups. And if you, I don't know if this is the case, but if you have already attended this conference, yrCSS, in the previous years, even just last year, it's likely that you have faced people working with proximity data or face-to-face interaction data and things like this. For instance, here I mentioned just one, maybe the first big study that was done on the topic, social pattern collaborations, which has been going on for over a decade so far. And the idea is that people are given sensors. If you're close enough, or even better, if you're facing each other, you should get a link. But the thing is that in some cases, here we have time-resolved data. So in some cases, actually, these are not really links. These are actually simplices that we want to model. And the idea is that actually, if three people are meeting at the same time or speaking to each other, we should model this as a three-body interaction, not as a collection of a triangle. So in this case, actually, it's easy to distinguish between the filled triangle or the empty triangle. So one thing that we wanted to have a look at was actually the distribution of these interactions in real-world systems, face-to-face interaction networks. What we see is that in all these systems, which are traditional data sets which have been analyzed by these people, actually most of the interactions are dyadic, but we have enough group interactions. For instance, in these data sets, friends and family, from interaction data sets from university residents, we have groups which are even very large, more than 10 people at a time. Probably people were having a party in the residence, something like this. And what we see is that actually, we saw that actually these people, the occurrences, and we were interested in, I don't know, the patterns of these groups. And what we saw is that actually you have burstiness, which is something that is very well known for human activity and even for pairwise interactions. And we saw that for groups is the same. So what does burstiness mean? It means that actually there are some events which tend to be extremely correlated. And then you have big breaks between them. So this is not only true for pairwise interactions, but this is true also for larger groups. And you can do a sort of a dual measure for this, which is where you do not look at the breaks, but basically you look at the length of each group interaction. And this is what is called a train of events. So you look at how many consecutive interactions of one type you have. And if we try to compute this, if we try to compute the probability to have a train of interactions for groups of size 2, groups of size 3, also groups of size 4 and larger, where we had the statistics, what we see is that we see the emergence of this heavy-tailed distribution. So this means that indeed, you know, there are some groups that tend to stay together for much longer than expected. There is a lot of memory into the system, even if we have not yet analyzed this with the tool, how this analysis of memory and non-Markovianity have been done into the system. I just want to show you the comparison. For instance, the comparison with the empty squares, if you can see that. That would be the system without any memory. So that is a system where we have reshuffled the events, and basically follows a Poisson distribution if the case very, very quickly. And the behavior of the real data is very different. And in particular, what is going on? Well, what we saw is that actually there is a sort of a temporal reinforcement effect. So if there is a group, for instance, a triangle, a group of 3 people, and it is quite possible that it breaks down at the very beginning. Okay, maybe it was just people who met by chance. However, if they tend to stick together, and actually the longer they stick together, the higher will be the probability that the group is not going to break. So this is a sort of a temporal reinforcement feature of all these real-world systems that we saw. And yeah, I think somehow it opens up the idea to investigate the presence of memory and non-Markovianity into our higher order social systems. Another very simple example, again, basic measure, is a similar data set, but from ecology. So this is a group of guinea fowls, and this was done in collaboration with some ecologists, because I'm not an ecologist, unfortunately, because maybe it would be more fun. And the idea is that they spent a lot of time doing fieldwork, and they assigned GPS to the guinea fowls, and we can study somehow the group dynamics of this animal. And you can suddenly, right? I mean, these people have done this for a long time, but again, just looking at pairwise interactions. Here, I just want to give you the type of very simple insights, but new insights that you can get with a group analysis. So, for instance, how about the patterns of connections of males and females? Well, here I'm counting the number of different hyperlinks of size 2, meaning just the number of other single individuals, the number of pairwise links that a male and a female can have. And yeah, it's 24 just because there are 25 animals into the system. So you can meet at most 24, and every guinea fowl at some point has met somebody else. And these numbers are quite similar. So if we consider groups of size 3, it doesn't seem that there is a big difference between males and females. But then this difference is very clear when we start considering larger groups. So it seems that females somehow males are much more mixed, have a much higher mixed membership pattern. So they roam around, they change groups all the time. And this is much less true for females. Okay. And then if we also go and have a look at how much time the guinea fowls spend together, what we see is that females like to spend a lot of time as pairs. So for instance, there is a single pair of females who is the pair of guinea fowls who was observed to be together as a pair the most. And instead, what we saw is that males spend much more time in larger groups. So they are somehow more relevant in the formation of these medium-sized groups, which are also a big part of the social activity of our groups of guinea fowls. Okay, so I mean, these are not really formal measures, right? These are just basic observations onto the system. I want to show you what we can do with some more formal measures that you can introduce. So most of you are probably already familiar with network motifs, which I also mentioned at the beginning. So they have been long been considered the building blocks of complex networks, because studying them allows us to understand things about the functionality of the system. So what are they? Well, they are small patterns. For instance, this is how they were originally introduced in the original framework in the paper by Uri Alon and collaborators in 2002, where they looked at patterns of free nodes and directed connections. So you have these different 13 building blocks, and you can study how frequent they are compared to what expected by chance, compared to a suitable null model. And yes, you can compute their frequency, their abundance. You can discount it by what expected by chance. And actually what you can do is that you can take the frequency of each motif and put all the frequencies together, build a chain of these normalized frequencies, which is what is known as a significant profile. And what they saw, which is very cool, is that actually motifs belonging to different domains have a similar significance profile. And this is why people also believe that studying motifs is important for the functionality of a system. So here there are the 13 motifs ordered, and clearly different types of social networks or non-social networks align into different classes. So this is just the same information represented as a correlation matrix between the different superfamilies of real-world networks. Each block would be a superfamily. So motifs have long been extended to account for more complicated things, for weights into the systems, temporality, multiplexity. How does it work with higher order systems? Well, first of all, let us forget about direction, because it becomes a very complicated problem. And even just let us consider groups of free nodes. So we have these 6 types of different ways in which nodes can interact. So they can interact as an open triad or a closed triangle without any group interaction. This is basically the traditional 2 motifs that we can have as a free body interactions without the group interactions. But then we can also have just group interactions. So for instance, that could be 3 people who decided to write a paper together as a triplet, but not in any pairs. And then we can have superpositions of these group interactions and pairwise interactions. The important thing is that this pattern of interactions should be connected. I don't know if I mentioned this at the beginning, but this comes with the definition of what a motif is. How many patterns there are with 4 nodes? Does somebody want to guess? A lot, of course. This is why I was asking. So there are 171, and then with 9 nodes, it is impossible. It grows super quickly. So I mean, of course, there are some computational challenges while doing this. This is already why we had to get rid of interactions. By the way, I think it would be very interesting to study motifs with interactions. It has to do with this concept of broadcasting. You know, you speaking to many, or many, you receiving the opposite. You receiving multiple inputs from other people at the same time. There are some special data sets where you can have this type of information. But for the moment, we decided to stick with the simple thing. And what we saw is that we saw something similar to what the group of Uri alone had seen. So here, for instance, we have our 6 higher order motifs that I'm labeling here from 1 to 6. And what we saw is that by analyzing some 25 different higher order data sets, which are basically the ones that were available in the literature until a year ago or so, we see that different families, networks of different domains tend to cluster together. And in particular, we observed these 2 blocks. One which had to do more with social interaction, so similar to the data sets of social pattern that we saw before. And another one which had to do with co-authorship networks across different domains. It was a quite stable signal. And also with some biological data set. So I think it's a bit clear what is going on if we analyze, if we look at the most frequent motifs which are found from for motifs of size 4. So what we saw is that in the biological and co-authorship networks, we had a lot of these large group interactions without necessarily a lot of other nested interactions in it. So not a lot of pairwise interactions in it. Well, this was quite different from these face-to-face interactions. So in social systems, in a lot of social systems, also in emails, technology here was like some data sets on emails. What we saw is that if there is a group interactions, a group communications, often case, actually, there are also interactions at the smaller levels. So we interact as a group, but I also talk individually to the single people in an office, in a hospital, in a school. And I mean, this type of a way the system is structured is quite different from co-authorship networks. Even if you think about the co-authorship patterns of yourself, your supervisor, or your collaborators, you will see that in a lot of cases there are a lot of combinations which are unique. Or maybe there are a lot of people who like to work as a team of 3, but not necessarily as a they never worked as a team of 2, for instance. And the same is true for biological data set. So I think there are some interactions that work, for instance, to build a medicine. There are some interactions of 3 things that work. But if you just combine 2 of them, it doesn't give you any good antibiotic, for instance, or something like this. So this was just a way to identify a signature at the local scale, very simple signature of how these higher order systems may be assembled in different ways. And I wanted to have a little bit, I was interested, so this is the same correlation matrices actually that I was showing before for free from motifs of order 3. Here is from motifs of order 4, so we have a bit more information. This is a bit more fine grained. So I was interested about this nestedness of the interactions, no? And I thought, let's go and study something else, something similar to temporal reinforcement that I was talking about before. But this has to do with structural reinforcement. So basically, first I have this. So just let me show you. This is another characterization of this nestedness of the interactions. So for these social interactions, given an interactions which is very large, typically we have a lot of interactions inside it, and a lot of these interactions are small. So the average size of the nested edges will be small. We have exactly the opposite pattern in this co-authorship biological network. So we write a paper as a group of 6, maybe it's just the 6 of us, right? There are no small subgroups contained in it. And when there are, they're large, because maybe we write a paper in a group of 6, then somebody leaves, so it's just 5 of us, and the nested hyperedge is still very large. So I was interested in this type of reinforcement. So I thought, okay, we have a group interactions. For instance, an interactions among the 3 people. Does the presence of pairwise interactions among the same individuals make the group interaction stronger? So this is a simple question that we had. So what we did is that we ranked our group interactions from a pure group interactions with no pairwise interactions, and then we consider the motifs where we started adding pairwise interactions into them. And here on the y-axis, what we checked for all these different data sets about face-to-face interactions was the intensity of the group interactions. How many times actually these group interactions were observed into the different motifs. And what we saw, with some fluctuations, of course, I mean, but the general trend is that the more pairwise links you have within your group interactions, the stronger will be the group interaction. The more stable somehow is this building block. And in some cases, for the high school data set, it's interesting because there are also information about people who declare to be friends with each other, or if they are friends on Facebook and so on. So we basically try to look at the same. We look for how many, so as a function of the different nested group interactions, we looked at the probability that they also declared the average number of friends within these groups, both from a survey and from Facebook data. And also in that case, we see a growing trend. So somehow this nested structure supports stable group interactions. And maybe, yeah, this is just how social networks are organized in the real world. How much time do I have? 15 minutes, something like this. 12 minutes. No, it's 12 now, yes. Yeah. Okay, so I want to talk about something very different now, which is a different type of data. Different type of data which are recorded in the form of a time series, and these are data that we see every day. I don't know if there is anybody here who works with financial systems, for instance, and looks at how stock prices fluctuate over time, or of course human brain is a big example. But we also have, I don't know, information about ecological systems, like records of temperature, water levels, pollutions, all such type of data. And I mean, as I was saying at the beginning, people have studied for a long time the correlations among these time series, if there is a causality also that can be inferred from time series. And a shortcoming, I think, of this, as I said at the beginning, is that most of these approaches, not all approaches exactly, but most approaches are mainly based on pairwise connections. So basically, if, for instance, we have fMRI data, which is a measure to quantify the activity of the different regions of the brain. We have time series that can go up and down, and basically, if regions tend to activate together, we will put a functional link. You can compute the significance level of this link. You can do many things, but in the end, you will have a link which is possibly weighted, but a link is a link and only puts into relation two nodes at a time. So these are about building what is known as functional connectivity in the brain, but there are similar analysis done for financial markets, for instance. But the questions that we had was this one. Is the information encoded in multivariate time series coming from loanness, like loan behavior, true pairwise behavior, or some group interactions? And in particular, is it possible to infer higher order dependencies into the system just by looking at time series? So can we infer statistically significant groups in our correlated structure of time series? So I think this is actually a very natural question to ask. And not a lot of people have thought about trying to answer this. But I think sometimes an idea seems obvious only because now we have started working with these higher order networks. And so to us, it was a very natural question. And the problem is the following. So the idea is that these are our multivariate time series. We have many time series at the same time. For instance, these are time series associated to the different brain regions. And what one can do is that one can study basically the co-fluctuations of these time series. For instance, there is this paper in Nature Neuroscience, very recent, from a couple of years ago, by Rick Betzel and collaborators. And this was their idea, was let's build what they called an edge functional connectivity structure. So we just build all the edges, and we try to understand what type of new information is into the system. And they've done a lot of work with this. And in parallel, actually, we were developing something similar, but we were already thinking to go higher order. So the idea is that why shall we stop at the level of edges? No, we can do the same at the level of triangles, right? So I'm trying to build two simplex and trying to build a field triangle by looking at the co-fluctuations patterns of 3 regions at a time. And yes, what we do, there are some technical tips. So for instance, one thing is that we rescale all the pairwise edges that we observe across time with a z-score just to normalize the signal, and we do the same for all the triangles. Otherwise, it would be difficult to compare the magnitude, the intensity of the strength of the triangular interactions against the pairwise interaction, just because you are multiplying 3 objects which are between 0, 0, and 1, or some numbers anyway. So this is a small technical tip. And another problem is how to define coherence. So when we multiply 2 time series, plus and plus will give you a plus, minus and minus will also give you a minus. So in that case, to identify coherence is easy. In a triplets, it's not the same, because basically when you multiply minus, minus, and minus, you get a minus. But we decided actually to apply what we call a pure coherence rule. So if all 3 time series are up, then we assign a positive edge to a positive sign to the triangle. Otherwise, we assign a negative edge. So there are these small technical things to understand. But what is the question that we had? The question is, can we identify triangles, okay, which co-fluctuate more than what expected by looking at the pairwise co-fluctuations into the system? So this is a very simple question. So we want to understand, are there regions are the groups of brain regions, or in general, not only brain regions, it could be anything. It could be financial data. It could be any dynamical system into your system. You can do this with the Kuramoto model, with any types of oscillating system. Can we identify triangles which oscillate more than their pairwise subfaces? And do we get new information by doing this? So, okay, so I mean, there are a lot of possible triangles that you have to compute. And in general, the approach is scalable to groups of any size. Of course, it takes a lot of time. So what I'm going to show you is that actually it makes sense to do this, because if it was not making sense, it wouldn't be a very good tool, because it is more computationally expensive, of course, than a traditional time series analysis. So what we do basically is that once we have rescaled all our interactions and we have all our edges and all our triangles, we sort them and we try to add them, starting from the ones with the highest weight to the ones with the lowest weight. And if at some point we add a triangle into this procedure whose corresponding edges is not there, it means that this triangle is co-fluctuating faster than the pairwise interaction. So this is one of the triangles which is interesting to us. So what we do is that in the end we perform these operations and we collect all these triangles which are there. For instance, we can even simply compute the fraction of triangles which are there, which oscillate faster than the pairwise subfaces. And this tells us it's a very simple measure of how much higher order the system is. If there are no triangles which oscillate faster than the pairwise connection, the system is really not higher order. So you can just analyze it with traditional tools. If there are a lot of triangles which oscillate much faster than their pairwise connections, it means that the system is truly higher order. So functional connectivity approaches are really not very good to understand and analyze the system. So we can define, for instance, this hypercoherence indicator. which is simply the ratio between coherent triangles and hypercoherent triangles, co-fluctuating triangles, and the total number of these triangles. And we tested this on simple dynamical systems, like these couple math lattices, which are particular dynamical systems where we can tune different regimes. So this is a very well-known study where over time, depending on the parameter of the system, you can have something which is very chaotic and complicated like this, fully developed spatio-temporal chaos, or something very regular, okay, like these other things. And what I'm showing you here is that here, over time, basically, we change the dynamical regime into this. So basically, we create, we produce different patterns, and these simple, very simple indicators, hypercoherent indicators, actually successfully distinguish all these different regimes, and it does so by ranking them in the right order, from more ordered regimes to more disordered regimes. And what is very nice is that it might seem so simple, but actually if you compare traditional approaches and even not so traditional approaches, indeed, if you compare every single other approach that the reviewer has asked us to do, you do not get this very simple ranking. So this is a case where I'm showing you that this machinery, which is a bit more complicated, actually gives you more information into the system. And then what you can do is that once you have this machinery that you know it gives you more information, you can go and study, for instance, financial systems, and you see that there are some moments of ultra synchronization where these are typically financial crises, when a lot of things go down together. Or in the brain, there are entire regions that are ultra synchronized. Of course, some of these things, I mean, we know from different studies, but here we are recovering this information in another way. And I don't want to spoil too much of this, because if you're interested, there is the talk by Andrea on Friday at the main conference. So this was just to give you a short review. And also, we do not do, in the original paper, we do not do only this very simple measure of hypercoherence. We also do some other slightly more complicated things. But I mean, I think this was a good example to give you, to show you how a very simple higher order measure can unveil new information with respect to pairwise analysis. So to conclude, I want to say something. So non-pairwise interactions are not an entirely new idea in physics. This you will hear a lot. True, absolutely, absolutely true. For instance, I don't know, from many body field theory, spin models, and so on. What's the new idea in physics here? Well, the idea is that we still want to keep all the tools of network scientists. Now, we are as network scientists, we are interested in multi-scale complexity at the different scales, community structures, homophily, core periphery structures, sortativity, all these type of things. So we are not losing this, right? We want to keep the richness of this. And it is true that people have studied since a while, for instance, spin models where you are coupled with other people, but these are typically done in well-mixed scheme or in an all-to-all scheme. So like Kuramoto model, where I interact in groups of 3 with everybody, rather than groups of 2. So the idea is that here we want to structured higher order interactions, and I think this is a new thing that people have been trying to do in the last 3-4 years. And another thing is that people from different backgrounds have thought about this. Absolutely true. For instance, in this nice book that from Stanley Wasserman and Katrin Faust, that probably some of you know, it's like one of the Bible of social network analysis. There is one chapter which is about higher order, it's about hypergraphs. But as I say, if you see, they have a very simple idea to model a party of 1, 2, 3, 6 people. Okay, groups of children playing at a party, 6 people. So why? I mean, what we do in the end is a data-driven network science, data-driven complexity science. So it's with the coming of all this new, much more refined, much more fine-grained data that actually this became interesting. The same way I think as it happened with temporality. It's not that people didn't know about temporality before 2008. People knew, but we did not have the right data to get new insights. And mathematical frameworks, simplicial complexes and hypergraphs. This is from the maths community. These things have been there for a while. Simplicial complexes, I mentioned one book is from 1956. This is a famous book on graphs and hypergraphs from 1973. So the question is really, why did it take us so long? And I think because it's hard. It's hard because a lot of things are much more complicated. If you are from physics, you know that the two-body problem is solved, the three-body problem is not solved. So when you try to describe mathematically the dynamics, the structure of things with more than two bodies interacting at a time, it suddenly becomes much more complex and complicated. But I think now we are up to the task, and there is a whole community working on this. It's not only me or my collaborators, but it's a lot of people working on this, which I think is an interesting topic. Last word is, I think these higher order tools are cool. They make sense. Be conscious when you do higher order analysis, because higher order also means more memory to store the data, more complicated algorithms to analyze the data, slower analysis. Some of these codes might take a long time. Okay, so always have very clear in your mind the question: do we really need to preserve all this information? Do we need to store the data as higher order data? Can we just work with the projected data and pairwise data? And because of course we want to make our frameworks and models more complicated only if this is meaningful. Otherwise, we are very happy with the most basic models which describe well our system. And I think, since I'm running out of time, I think this is it. And thank you very much for your attention.